Okay, let's look at acid-base properties of oxides and hydroxides. We were already looking at oxyacids before. Solubility of ionic compounds may also be increased when dissolution is coupled to formation of complex ion. For example, aluminum hydroxide, aluminum AlOH3 dissolves in solution of sodium hydroxide or other strong base because of formation of complex ion AlOH4-. Equations for dissolution of aluminum hydroxide, formation of complex ion, and combined net equation are shown below. As indicated by a relatively large value of equilibrium constant, coupling complex formation drastically increases solubility of aluminum hydroxide. So solid aluminum hydroxide can make aluminum 3 plus ion and 3 hydroxide, its solubility product. Another reaction is aluminum with 4 hydroxides making complex ion. Formation constant is this one. And net reaction, it's addition of 2 and it have positive and big complex. Well, in other words, aluminum hydroxide is amphoteric. In acid, it acts as Bronsted-Lowry base by picking up hydrogen ions and neutralizing the acid. So aluminum hydroxide as a base reacts with acid, making salt and water. In bases, it acts as Lewis acid by taking electron pair from hydroxide ions. Same aluminum hydroxide reacts with hydroxide to making AlOH4- ions. So two opposite functions, that's what we name amphoteric. Well, this is a last case is very interesting, so I'll remind you what we name acidic, basic, or amphoteric compounds. Acidic hydroxide of element E has OH group that can donate protons. So OH bond breaks and H plus ion is released. Acid donates proton. If hydroxide is basic, EOH group breaks EO bond right here. And so these species can donate hydroxide ion. Now, amphoteric can do both. They can do basic breaking or they can do acidic breaking. Let's look at first periods of periodic system. First, water molecule is neutral, but it can undergo some dissociation, as you remember. Now, what happens to first group elements? They have very low electronegativity, and they are all basic. Lithium hydroxide and sodium hydroxide, and below that potassium, are all basic hydroxide. Now coming to group number 2, electronegativity increases and beryllium hydroxide is amphoteric. Below that, magnesium has lower electronegativity and magnesium hydroxide is basic, but it's weak base. Solubility is very low. Going to group number 3, boron makes BO3 very weak acid, boric acid. Sometimes we write not BOH3 but H3BO3, same compound. Now aluminum has electronegativity similar to what of beryllium. That's why it has lots of properties similar to beryllium, and aluminum hydroxide is amphoteric. We have seen that in previous slide. Next is carbon, and carbonic acid has one terminal oxygen, so it's usual weak acid, well known. Silicon again has a lower electronegativity, somehow similar to boron, so SiOH4 is very weak acid. Practically no acidity in both of these cases. Going further to nitrogen, electronegativity is even higher, and nitric acid is strong acid. Now phosphorus has much lower electronegativity, and phosphoric acid is weak acid. It's only one terminal oxygen here. There are no element OH compounds for oxygen and fluorine, but we have sulfuric acid for sulfur, which is strong, and perchloric acid, which is even stronger. So acidity is going from left to right in periodic table. It's going slightly lower down periodic table, so acidity is higher with a smaller number of periods. Examples of reactions: sodium hydroxide, basic, makes Na plus on OH minus 100% yield. Beryllium hydroxide is very little soluble, but it can give B2 plus ions and 2 hydroxides. At the other hand, beryllium hydroxide can react with 2 more hydroxides to make tetrahydroxoberylate, so it's complex ion, similar to what we have seen with aluminum. Aluminum hydroxide can make aluminum 3 plus ion and 3 hydroxide, or it can take 1 hydroxide to make negative ion, similar to beryllium. Now nitric acid dissociates as strong acid, making proton and nitrate. Perchloric acid makes proton and perchlorate. Weak phosphoric acid makes 1 proton and dihydrogen phosphate ion. It can undergo further dissociation later. Very similar properties are of oxides. We name acidic oxide that reacts with water and donates proton. It is a Lewis acid. Basic oxide reacts with water and accepts proton, making OH minus. It reacts with acidic oxides. Acidic oxides reacts with basic, basic with acidics. Now let's look. Lithium and sodium oxides are basic. Beryllium oxide and aluminum oxide are amphoteric. Very weakly basic is magnesium oxide, but visibly basic. Very weakly acidic are boron and silicon oxide. Weakly acidic carbon dioxide and phosphorus oxide, P4O10. It's a large complex molecule. Strongly acidic oxides are N2O5, SO3, and Cl2O7. Let's look at some examples of this. Sodium oxide reacts with water to make in sodium hydroxide solution. Beryllium oxide reacts with acids to make beryllium ions, chloride ions, and water. On the other hand, beryllium oxide can react with sodium oxide to make berylates, Na2BeO2. Aluminum oxide, similar to beryllium, reacts with HCl to make aluminum ions, chloride ions, and water, so making aluminum trichloride salt. On the other hand, aluminum oxide can react with sodium oxide to make sodium aluminate. So aluminum and beryllium are amphoteric. Basic magnesium oxide reacts with acidic CO2 to make magnesium carbonate. Acidic SiO2 reacts with strongly basic Na2O to make sodium silicate salt. Phosphorus oxide reacts with water to make phosphoric acid. And the last, calcium oxide, reacts with sulfur trioxide to make calcium sulfate. So again, we have increase of acidity from group number 1 to group number 7, and increase of acidity when we are going from below to above in the same group.